All right, so in this video, we are going to be talking about a topic called thermodynamics. I'm going to be giving you all an introduction to this type of physics, and we'll be learning about heat and energy and how to calculate the heat in a system. So our objective for this video, and I'll zoom in so we can read it, is to be able to describe the movement of thermal energy through conduction, convection, and radiation. Our essential question that you all should try to answer in about a 1 to 2 sentence summary at the end of this video is, what is heat and how does it move? So let's quickly just define what thermodynamics is, because I know that it's kind of a long word. It might be a word that you are not familiar with. So thermodynamics describes the study, or it is the study of the relationship and interactions between heat, temperature, work, and energy. Now, when I also talk about work and energy, we are thinking about the physics definitions of work and energy that we have learned earlier in the year. So thermodynamics is looking at all of these relationships, and it's very useful to us because it can explain a lot of phenomena that occur in our natural world. So there are a couple terms that we must go ahead and define before we begin our discussion on thermodynamics. That the first term is temperature. Now I know what y'all are thinking, and that is, well, I already know what temperature means, but what I want to give you is the physics definition of temperature. We're very familiar with the word temperature describing how hot or cold something is. But in physics, we're going to take this one step further, because temperature, what it really is describing is it's a measure of the kinetic energy of particles. So typically, when we are measuring the temperature outside, we are measuring the amount of kinetic energy each air particle has. So again, we're kind of bringing back these concepts of energy and work in our thermodynamics discussion. Now, our variable for temperature is a capital T, so that should be somewhat easy to remember. Our unit of measurement. Now, the typical unit of measurement we use in physics is called Kelvin. We use a capital K for Kelvin. But we do sometimes use Celsius as well. So I've included both on here. You all might be more familiar with Celsius, but Kelvin is our pretty standard unit of measurement for temperature. So as you can kind of see, I've tried to draw a little depiction of how temperature affects the kinetic energy of the particles. So I want you to imagine that you are a particle, and it's hot, it's really cold outside, temperatures are low. When it's cold outside, you don't really feel like doing anything, right? You're kind of just sitting there bundled up, shivering, waiting for it to warm up. Same thing happens with these particles. These particles are like, this is way too cold. We have very little kinetic energy. We don't feel like bouncing around. We are not super excited about this cold temperature. So again, these particles do not have a lot of kinetic energy at a low temperature. However, at a high temperature, what that's describing is that these particles all of a sudden have a lot more energy. Just like when it's nice and pleasant outside, you are a lot more motivated to go run around. Especially as a kid, you're a lot more motivated to go run around on the playground when the weather's nice outside. Same thing happens with our particles of matter. Again, at higher temperatures, they're going to have higher kinetic energy. So that is temperature. Now, I do want to point out, temperature is different from heat. So notice there are two different definitions for temperature and heat. Heat is defined as the energy transferred from one object to another as a result of differences in temperature. So the main thing I want you all to realize here is heat is another form of energy. It is thermal energy. So our variable for heat, when we get to our equations, is a capital letter Q. So please remember, this is a capital letter Q, not our lowercase q, which we use as our variable for charge, electric charge. We're going to use a capital letter Q for heat. Now, since heat is energy, our unit of measurement for energy is in joules. But for heat specifically, when we talk about thermodynamics, we can also measure heat in calories. So both of these are units of energy that you all should be familiar with. That is how we will be measuring heat for our thermodynamic calculations. So moving on from heat and those definitions, let's talk about how heat behaves and how it is transferred between objects. So one key concept that I've put in red here with a big star by it is that heat will always flow from hot to cold until the system is the same temperature, right? So heat is going to try to flow to its colder areas to, reach what we call thermal equilibrium so that objects are the same temperature. And we'll talk a little bit more about thermal equilibrium in our next video. But again, key concept here is that heat will flow from hot to cold. So with that in mind, that gives us several behaviors of heat and how heat is transferred. The first one is conduction. So you all are probably pretty familiar with conduction, right? We've talked about electrical conductors in our electricity unit. Same thing happens with heat conductors. So energy is transferred through direct contact via conduction. So you'll notice if you've ever held a pot over the stove or been cooking before, you start to see over a gas or electrical stove, the heat from the stove is going to rise throughout the metal pot and eventually reach your hand. So if you have a very good conduction going on in that metal pot or pan that you're using to cook with, you might want to wear gloves. So that is the conduction of heat via direct contact. Now, convection is another unique way of transferring heat. So in convection, what's happening is that the particles in a liquid or a gas, and I do want to be specific that it is happening in liquids or gases, are moving and kind of creating this convection current, which I've kind of depicted in a circular motion here, due to differences in density and temperature of those particles. So if you've ever studied maybe something about the weather, right, we know that warm air rises. It tends to rise because it is less dense than cool air. So the heat is actually moved. And again, we know, so warm air rises because it's less dense. And we also know that heat moves from hot to cold. So we kind of get this circular red arrow moving up and to the left in our convection current. Now, cool air is more dense, so it's going to fall under the hot air. And it also is going to be, we'll actually start to see that it starts to form this kind of cyclical current as a result of cool air falling and then hot air rising and trying to replace that cool air. So we see this unique aspect of convection current. Next term we will go over, this is our final way of transferring heat, is radiation. All right, so radiation is simply energy transferred via electromagnetic waves. We know electromagnetic waves an example of that would be a light wave. So we have the sun, right? The sun has a lot of electromagnetic waves, right? It provides us with light, like visible light. It also transmits UV rays, which are another example of electromagnetic waves. So you'll see when we, it's typically warmer out in the sun outside than it is in the shade. And that is because of radiation. So now that we've kind of defined how, what heat and temperature are, we've talked about how heat moves and its general behavior. Let's talk about how to calculate heat. Now here is our equation for calculating heat. So remember, I said that a capital Q is our variable for heat. We always use a lowercase m to represent mass. And we are going to add a new variable, which is what we call the specific heat capacity. Now notice we are using a lowercase c for our specific heat capacity. Now I know that we use another lowercase c for a constant, which is the speed of light. We already know that the speed of light is equal to a specific number. This lowercase c is going to be a variable, meaning that it can change. That number that the c is representing could be anything. All right, and then lastly, we are going to use temperature as well to calculate heat. So our change in temperature, notice how we're using the delta sign, which means change, and a capital T for temperature. Now, really quickly, y'all might be wondering, what is specific heat capacity? So remember that some objects are better at holding heat than others, right? Some objects are better at heating up very quickly than other objects. So that's kind of what the specific heat capacity of an object describes, is the amount of energy required to raise the temperature of that object. Specifically, it's the amount of energy required to raise 1 kilogram of that object or substance by 1 degree Celsius. Now, another trend I do want to point out, and this may seem pretty intuitive, but I do want to just point that out, is that heat can be positive or negative from this equation. So anytime we see that heat is positive, it means that the system, whatever we are calculating, or that substance that's being heated, is gaining energy or heat specifically. So that positive heat value means that the temperature of that object is going up. It's gaining heat or energy to itself. In contrast with when we see a negative Q value, a negative number for heat, it means that that object or substance is losing energy. It's losing that thermal energy or heat. So we will run through an example here so we can kind of see this in action. So this, and we're going to run through all of our steps to solving a physics word problem as well, so we can kind of see how this plays out in a real world example. So what we have is some cooking oil. And again, I'm not going to, I'll just draw our pan here if we were cooking. We're cooking over a stovetop, and our cooking oil, right? We've got 2.5 kilograms of cooking oil. That's actually quite a bit of cooking oil. So one thing I do want to point out, though, is that we've got a couple numbers here. We'll go ahead and put that in our drawing. The first one is the mass of the cooking oil. So we've got, I'm on the highlighter mode. So again, 2.5 kilograms. Remember, kilograms is our unit of measurement for mass. So we'll go ahead and record that the mass is equal to 2.5 kilograms. We also see that there's a specific heat capacity. So remember, we're using C to represent specific heat capacity. And C is going to be equal to, for our cooking oil, 2200. And now the unit of measurement for our specific heat capacity in this problem is joules per kilogram degree Celsius. Again, I don't want y'all to think too much about this unit of measurement. Main thing I want you all to see is that the specific heat capacity is about 2,200. Right, and then the last thing we are taking note of is our temperature, or specifically our change in temperature. So we should be seeing that it is being heated from 25 degrees Celsius to 100 degrees Celsius. So what we can actually do here is, while we have two numbers, right, but we are looking for our change in temperature, right? We want to know how much that temperature has changed. So it has changed from 25 degrees to 100 degrees. So overall, the difference between 25 to 100 degrees Celsius is 75 degrees Celsius. So we can just go ahead and do that quick calculation there. So really quickly, I will rewrite this in our T-chart so we can kind of keep track of all of our variables. And I know I'm writing into that summary space, so I hope you all, if you need to go on to the next page of your notes, that is totally fine. But again, we've got M is equal to 2.5 kilograms. C is equal to 2200 joules per kilogram degree Celsius, and our change in temperature is equal to 75 degrees Celsius. Now, the last thing I do want to point out is this problem is asking how much energy. Now, this might throw some people off, but remember that energy is really just another word for heat when we talk about thermodynamics. So what we are really solving for is Q, or the heat. The heat required to raise the temperature of cooking oil from 25 degrees to 100 degrees Celsius. So let's go ahead and move on to step number 3. We'll set up our equation. We are going to use our equation to calculate heat, which is written as Q equals MC delta T. I like that equation because it rhymes. And now let's go ahead and plug in some of our numbers here. So we know that we are going to be plugging in our mass. I will rewrite this so we can go ahead. Again, our equation's set up properly, so we can go ahead and start plugging those numbers in. Our mass is 2.5. That is going to be multiplied by our specific heat, which we know is 2200. And that is that's going to be multiplied by delta T, which we know is 75 degrees. All right, now we've got this all plugged in, and again, I'll give y'all a second to plug this in your calculator. And hopefully you got an answer similar to mine, which was 412,500. So 412,500 joules of heat. So that was quite a bit of heat and energy required to heat up 2.5 kilograms of cooking oil to about 75 degrees in temperature. So that is kind of how we're going to use that equation for calculating heat. Again, I'll just go ahead and zoom out so we can kind of review all that we have learned in this video. Again, please make sure you all are writing your summaries, about 1 to 2 sentences, trying to answer that essential question at the end of this video. So hopefully that gave you all a good introduction to heat and temperature and how to calculate heat and just some very basics of thermodynamics. I look forward to discussing this with you all more in class.